Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 9 on the volumes of right prisms and cylinders. So we're going to really get into a lot of volume work now. And volume, just like area, is a little bit confusing. So let's get into it with the easiest and earliest thing you ever found the volume of. Here we go. Volumes measured in cubes. Perhaps the most important measurement for a solid is its volume, the amount of three-dimensional space inside the solid. Volume is often measured in terms of how many unit cubes fit inside the object. Now, I do want to point out, though, just for a moment, that unlike area and length, there's a lot of different ways that we measure volume besides using unit cubes. You know, there are things like the fluid ounce, the gallon, the pint, the cup, right? All of these things are different ways that we measure volume, and we'll see some of them as we go through the remainder of the lessons in this unit. But at least our formulas that compute volume are almost ones that measure how many cubes that are a unit size, i.e. their edge lengths are 1 centimeter by 1 centimeter by 1 centimeter or something like that, fit inside of the object. So let's calculate the volume one more time of a box. Here we go, exercise number 1. A rectangular right prism, otherwise known as a box, has a length of 8 inches, a width of 4 inches, and a height of 5 inches. Letter A, real simple. What is the area of the base of the box? Use appropriate units. Awesome. So pause the video now and come up with the area of the base of the box. I obviously gave you way more room here than you need, but take a minute to do that. All right, I think I'll use the big letter B for the area of the base. I don't know, maybe that's foreshadowing. So the area of the base, all right, is 8 inches by 4 inches. So the area of the base, obviously, is 32 square inches, or 32 inches squared. All right? And again, what's really cool, and hopefully this makes sense, is it means if we took these cubes, right, whose bases are just squares that are 1 inch by 1 inch, we could fit 32 of them just sitting on the bottom level of that box, right? 32 of them would nestle in there. Now let's take a look at letter B. What is the volume of the box? Use appropriate units, and then how can you use your answer from part A to determine the volume? All right, so in other words, right, here it is, right? All of these cubes fit into this box. How many of them are there? Pause the video now and see if you can figure this out. Well, there are 32 of them on this bottom level, right? 32 will sit right there. Okay, now, how many of those levels do we have? Well, each one of those levels is 1 inch high, and we have 5 total inches, so we get that 32, then we get another 32, and another 32, and another 32, etc. If I can stack them properly here, which I almost did, right? We have 5 levels of 32, okay? So we just get a volume of 32 square inches times 5 inches, whoops, and that's going to be, I think, 160, but let's just make sure, you bet, 160 cubic inches. Now, of course, you've learned for years that the volume of a box is length times width times height, right? You've learned this formula, volume equals length times width times height. And that is an absolutely great formula to know. But keep in mind, the reason that it works is that the length times the width, this, is simply the area of the base. And the area of the base, even though it is an area, actually tells us how many cubes, right? How many cubes, if I can remove that, apparently I can't. I think it's just not going to let me remove any of those cubes at this point. It tells me, I don't know, once they went there, they got stuck. The area of the base really tells me how many cubes we can lay that are 1 inch tall or 1 centimeter tall or whatever it is, 1 unit tall on the base level, right? That's this portion of it. Then the height tells me how many of those layers I have. So it should make all the sense in the world that we can calculate the volume of this thing by taking that area of the base and multiplying it by the height. Now again, if you're like, hey, I don't need to know that, I can just do length times width times height, that's fine, all right? But at the same time, there's a bigger picture here. And let's talk about that right now. The volume of right prisms. Although the procedure in exercise number 1 might seem like a formula, it is the very definition of volume. In other words, if we have a right prism, right, of any type, we can calculate its volume in the following way. Let's take a look. The volume is B times H, where B is the area of the base and H is the height of the prism. All right, this is really important, right? Remember, what a prism is an object that has sort of a constant cross-sectional area, all right? Right, the top and the bottom are the same, right? And then if it's a right prism, we just go up perpendicular between the two bases, right? And again, the area of that base is going to tell us how many cubes sit on the first level. The height will then tell me how many levels I have. So as long as I can figure out the area of that constant cross-section, I can then multiply it by the dimension that is perpendicular to it to get my total volume. Let's look at one that's a little bit more challenging than the last one, exercise number 2. A prism has a base that's an equilateral triangle whose sides measure 6 inches each. The height of the prism is 8 inches. What is the volume of the prism to the nearest cubic inch? All right, so just making sure that we understand this, right? We've got this prism, right? And its bases are equilateral triangles that are 6 inches each on a side, and then it's got a height of 8 inches. Let's just make sure that we've really got that cross-section, right? That cross-section that's constant looks like this. Now, ultimately speaking, it doesn't really matter what the cross-section looks like. I need to figure out what the area is, right? That's my big B for whatever reason. I wish it had been just like a big A with a sub B, but almost always they use a big B to stand for the area of the base. Once I have the area of the base, I can simply multiply it by the height of my prism, and I will have my volume. What I'd like you to do right now is pause the video now and see if you can think of a way to calculate the area of this equilateral triangle. Now, there's a couple ways to do it. All right. One way to do it is take an isosceles triangle approach, which is to break it into 2 right triangles and come up with its height using the Pythagorean theorem. And you could totally do that. And then once you know its height, then you can do 1/2 base times height and you have its area. There's nothing wrong with that. And if you went ahead and thought about that, that's great. But there is actually a slightly faster way, as long as we remember that an equilateral triangle has angles that are all 60 degrees. You see, if we remember that, then we can use that formula that says the area of a triangle is 1/2 AB times the sine of C, all right, where A and B are any 2 side lengths and C is the angle that's included between those 2 side lengths. So in this case, I'll use big B. My area of my base is going to be 1/2 6 times 6 times the sine of 60 degrees. That's going to be the area of my base. Now, I could go ahead and calculate what the area of my base is, or I could just say, hey, look, I'm going to have all of that and multiply it by 8. And that is going to be my volume. So ultimately, I'm going to do that all at once just to save myself some time, right? I have the 1/2 6 times 6, or you could even do 6 squared, that would work great, times 60 degrees. That is my big B, the area of my base, times my height, and that should get the job done. All right, let's bring out the calculator. Now I think what I'm going to do is I'm going to actually exit on the big screen right now just so that we can see this thing a little bit better. Okay, so let me just clear that out real quick. And let's do it, right? What we had is we had the area of the base, which was 1/2 times 6 times 6 times the sine of 60 degrees. All right, that's the area of my base. And then times my height, which was 8. All of that then results in a volume that is 124.707, etc. It's kind of an ugly number, but whatever. Let's see what they ask us to round to. We want to round to the nearest cubic inch, so that is going to be 125 cubic inches. Awesome. We'll get that down in just a sec. All right, let's keep that in front so that we can grab onto our calculator. Go back into full screen. Let's try that again. There we go. And let me just make sure, 125. And again, it's perfectly fair to take that isosceles triangle approach, come up with the height of this equilateral triangle. It would end up being 3 times radical 3, just for the record. All right, but it would be a little bit messy, okay, and you'd have to then do a few more steps. This is such a handy formula. If you've got a triangular cross-section and you know 2 sides and the angle in between, I would highly suggest using this formula unless for some reason they were like, express your volume in terms of radical form or something like that. Then it doesn't work quite as well. All right, let's keep going and working more with volume. Now let's talk a little bit about the volume of cylinders. Exercise number 3. A cylinder is a solid that follows the same rules as a prism because it has a constant cross-sectional shape and area. Explain why the volume of a right circular cylinder is given by V equals pi r squared times h. All right, so oftentimes this, let me write it a bit bigger, is a formula that you will be given, right? The tendency is to not give you the volume formula for a box or even the volume formula for a general prism. But a lot of times this one's given to you, and my claim is this is exactly the same formula as what we just had. Pause the video now and think about why that is. Well, it's pretty simple, right? Not just for a prism, but for any solid that has a constant cross-sectional area, we can say that the volume is equal to B times H, where B, right, is the area of the base. But the area of the base is simply the area of a circle, and that's pi r squared, right? So this part of the formula, pi r squared, is that part of the formula that's just telling us how many cubes, and I know that seems a little bit weird given that this is a circle, right? But how many cubes can sit on that circle? That's what that area tells me. Once I know how many cubes can sit on that bottom level of the circle, I multiply by h. That tells me how many cubes I can stack on top of each other, and I get my volume, right? So that's where this formula comes from. The area of the base is simply the pi r squared, all right? So it's really not a different formula than what we just used to calculate that triangular prism or what we used to calculate the volume of the rectangular prism. Anyway, let's take a look at one that's a little bit more challenging that puts a few different shapes together. Now, right prisms and cylinders arise in many real-world settings. Being fluent with calculating their volumes is a critical skill in geometry, and we are, trust me, going to get a lot of practice on it in the next few lessons. So let's take a look at kind of a cool, more sort of complicated problem. Exercise number 4. A pool is constructed that has a sloping bottom with a maximum depth of 8 feet and a minimum depth of 4 feet as shown. The width of the pool is 12 feet and its length is 20 feet. At the end of the pool is a wading pool in the shape of a half cylinder whose diameter is 12 feet. Letter A. Given the right prism portion of the pool, what shape serves as its base shaded on the diagram? All right, so I claim that this, without this portion is a right prism. But for a right prism, if we're going to want to calculate its volume, and you know we are, right, we need to know what shape is its base so we can calculate its area. Pause the video now and think about what shape is the base of this particular right prism. Well, here's the key, right? With any prism, right, you've got a lot of different faces. What you want to do is find two of them that are congruent. And the two faces that are congruent are sort of this front face that we see here and the one on the back side here. In other words, this right here is our base. And that can be tricky for students because a lot of times we think of prisms as sitting on their bases, but they don't have to, right? This shape, which is a trapezoid, right? And it's a trapezoid because this side, right, is parallel to this side, right? The other two sides aren't parallel, but that's fine, right? These two sides are parallel, but that would be a constant cross-section as we sort of moved this way along the pool. So we've got a trapezoid as its constant cross-sectional shape. Now, of course, to figure out the volume, we've got to be able to, in letter B, to determine the area of that base. So pause the video now and see if you can determine the area of that trapezoid. Well, I really like the trapezoid area formula, right? And the trapezoid area formula is 1/2 B1 plus B2 times H. Oh, so many H's, so many B's, right? Confusing, right? But keep in mind for a trapezoid, what that means is the two parallel sides, right? Those are our bases. And the height is the perpendicular distance between them, all right? Which is that 20 feet. Now, in other words, what we're doing is we're really averaging that 8-foot depth and that 4-foot depth, right? And then we're going to multiply it by that 20 feet there. This slant doesn't matter at all in terms of the area of that particular trapezoid. So the area of this trapezoid is going to be 1/2 times 8 plus 4 times 20. And that, if I did my math right in my head, will be 120 square feet. All right, now that we've got that area of that face, right, we can now think about what the volume of the prism portion of this pool is. So letter C. Determine the volume of the prism portion of the pool. Awesome. Well, why don't you go ahead and do that? Pause the video now and do that calculation. All right, well, all we need to do is take that area, right here, and multiply it by the dimension that is perpendicular to it, right? And that's that 12 feet there. So the volume now is going to be B times a different H, unfortunately, and that's going to be 120 square feet times, again, that perpendicular length right here or here, depending on how you want to look at it, and that's 12. Let's bring that out really quickly and get that down. 120 times 12, I think that's 1440, and it is. And that's 1440 cubic feet. That's a lot of water, but that makes sense. A pool has a lot of water in it. 1,440 cubic feet. Now, of course, we got to bring in that cylinder somehow. Let's take a look at letter D. Determine the total volume, including the wading pool. Express your answer to the nearest cubic foot. Now, obviously, to figure out the total volume, right, what we want to do is take the volume that we just calculated and add it to the volume of that half cylinder, all right? So let's talk about the volume of the half cylinder. We never even did a volume calculation with that cylinder, even though you did them back in middle school. So let's take a look, right? We know that the volume of a cylinder is pi r squared times h. In this case, of course, it's going to be 1/2 pi r squared times h. And you can really think about that as thinking about the area of that semicircle, or that semicircle, and then multiplying it by the height, which ends up being 4 feet. Now, to figure this out, we have to know what the radius is, okay? So pause the video right now, right? And see if you can sort of just, if at the bare minimum, substitute the correct numbers in here. You don't even need to figure out what that's going to be equal to. I don't think I'm going to. I'm going to actually eventually plug that expression into a sum with this one to come up with my final volume. But at least pause the video now and see if you can substitute the correct numbers into that. All right, well, we know that this dimension is 12 feet, which means this dimension is also 12 feet, which means the diameter of this cylinder is 12 feet, but its radius is actually 6 feet. Its height is that 4-foot depth right there. So the volume of my half cylinder will be given by 1/2 pi times 6 squared times 4, right? So my total volume will be equal to 1440 plus 1/2 pi times 6 squared times 4. And let's come up with that right now. All right, so we've got our 1440 plus every time, plus 1/2 times pi. Don't forget the pi. It's so easy to forget the pi. Times 6 squared times 4. And we get as our total volume to the nearest cubic foot 1,666 cubic feet. And again, when I can, I like to avoid writing out whatever messy answer that's going to be. I'd rather just take that expression, write down my final expression for the total volume, since I already knew the 1440, awesome, right? And then I let the calculator do the hard part. All right, nice compound shape, right? Multiple solids in there. All right, now anytime we have a solid with a constant cross-sectional area or shape in one direction, we can find its volume by multiplying the constant area by the length of the dimension perpendicular to that constant shape. So let's take a look at one that's a little bit less standard. Exercise number 5. A chicken coop is in the shape of the prism shown below. Determine the volume in cubic feet of the coop. Show the calculations that lead to your answer. All right. Well, what I'd like you to do is pause the video now and see if you can figure out this volume. And it is going to take a little bit of work, but thankfully there's going to be no pi involved because there's no circular cross sections here. All right, well, the real key, right, is that this image right here, right, which is the same as the front and the back of our chicken coop, right, that is our constant cross section. So the hardest part of this problem is figuring out its area. And honestly, to figure out the area of this pentagon, and it is a pentagon, right, because it's got 5 sides, right, what we need to do is we need to divide it up into a rectangle and a triangle. Now the rectangle is going to be really easy, right? So the rectangle is going to have an area of 10 feet times 7 feet. Yep, that's right. So that's going to be 70 square feet, but we'll wait for it right now. The upper portion, of course, is a triangle whose base is 10 feet and whose height is 4 feet. So the upper portion will have an area of 1/2 base times height, right? And all of that will then give me the area of that cross section. Let me figure that out real quick. I think I can do that, whoops, without having to use the calculator, I hope. And that's going to be 90 square feet, right? That's going to be the area of my cross section. Now, once I have that area of the cross section, I simply need to multiply it by the perpendicular length, right, between the two bases, and that happens to be 12 feet. So my volume now is going to be 90 square feet times 12 feet. That's going to give me cubic feet, and specifically, let's take a look. 90, whoops, not 90 plus, but 90 times 12, and that's going to be 1,080 cubic feet. Excellent. Nice. We don't need to round anything. There's no pi involved. Awesome. Let's take a look at letter B. If the entire volume of air must be moved out of the coop in an hour, how many cubic feet per minute must the fan move in order to accomplish this task? All right, so this is a nice rate problem, and I think you can probably imagine it, right? And again, if it's confusing because, oh, we're moving air out, imagine that you had, like, let's say a gymnasium that had 1,080 people in it, and all of them moved out over the span of 1 hour. And I said, well, how many people were leaving the gymnasium per minute? All right, I bet you could figure it out. So, try to solve this problem. All right, well, the rate is going to be simply the volume divided by the time. So the rate is going to be 1,080 cubic feet per 60 minutes. And now we just divide, right? Anytime we have a rate, we're just dividing a quantity by a certain amount of time. And we're going to find that we have to move 18 cubic feet per minute. And that's it. Awesome. Let's wrap this up. Now, we are going to be looking at numerous volume formulas, right, for the remainder of this unit. But the easiest ones to understand are those for right prisms and cylinders, or really anything that has a constant cross-sectional area. Whenever you have an object, right, that has two bases that are identical, right, then you can always find, assuming that all those cross-sections are identical to the two bases, right, you can always find its volume by simply finding the area of the base and multiplying it by the perpendicular distance between the two bases, all right? And it's actually it is not a formula, right? I claim that it is the very definition of volume, the very definition of even multiplication, right? The area of that base, one more time, tells you how many cubes you can stack on that lower level of the base, and then that perpendicular distance tells you how many sort of stacks you have, right? So yeah, figure out the area of the base and multiply it by the height, and you've got your volume. It's going to get a little bit more complicated when we look at things like cones and pyramids and spheres, all right? But we'll see those in upcoming lessons. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.